Well, hello everybody. Welcome to the week 7, is it? Week 7 review video. This is the glycolysis review video, and I couldn't be more excited actually. I'm super excited to be diving into glucose metabolism. Whenever I teach this course, which is rarely lately, I actually can't wait to get through the first unit so we can get to glucose metabolism. This, I think, is the richest part of the course. I can't explain to you and describe how excited I am. And if you're thinking to yourself right now, Dr. M, is it possible that you're really that geeky? My answer is yes, student. Yes, it is that possible. I really enjoy glucose metabolism this much. So what I thought would make sense, because a lot of your questions or feedback on the lecture videos was pretty much either no questions, you think you got it, but it's a lot. Heard a lot of that. Do we really need to know the enzymes? Which is yes. So just a general sense that it was feeling good for most of you, but a lot of information. And there is a lot of information. We have to set the stage, build the background, give you foundation, and describe glycolysis. So it seemed to me to make the most sense for this particular video was to just go through glycolysis again. But strip it down and get to the core fundamentals of what's going on in glycolysis. We'll touch on regulation, we'll definitely touch on reaction types, but just go through the process in all 10 steps, the biochemistry of the process, and describe what's going on. So that's what this video is going to be. It's just bare bones glycolysis, an overview of the entire pathway going from glucose to 2 molecules of pyruvate. So let's jump in. So what you're looking at on this, oh, and I should say a little bit different than most videos because I won't be drawing it by hand. We're really just going to be talking about reactions. So I just have the individual reactions as slides, and we'll describe what's most important about each one as we go through. So what you're looking at here, of course, is glucose, 6-membered ring of glucose. It could be the chair or the boat form, most likely the chair form because that's the most sterically favorable form. So we start off with glucose. And the very first reaction of glycolysis is step 1, which is catalyzed by this enzyme called hexokinase. Hexo for 6 carbon sugars, and kinase because it phosphorylates things. So this first reaction of glycolysis is a phosphorylation reaction. That's its reaction type. The phosphate donor is ATP, which we see over here, and it's donating a phosphate to glucose. So the end of that reaction is phosphorylated glucose, glucose that's phosphorylated on the 6th carbon, or glucose 6-phosphate. And the remnants of that ATP, now it's not adenosine triphosphate, it's adenosine diphosphate because it donated that 3rd phosphate group right here. That's the phosphate group that is on glucose. So that's pretty much it. A phosphorylation reaction catalyzed by hexokinase. The name tells you what it's doing. It's a kinase. It phosphorylates hexoses, or 3 carbon sugars. And maybe just a side little note here, this is an activation reaction. We talked about activating reactions along with coupled reactions either last week or the week before. Glucose tends to be fairly non-reactive because other than a few hydroxyls, it's largely non-polar. But once we put this big, very, very negative group on this 6 carbon, we've activated this glucose molecule. Now it's very heavily negative, it's very reactive, it wants to engage in chemistry. So that was really the main point. And the reason why this border here is blue is to remind us that this is the first regulated step of glycolysis. Hexokinase is subject to feedback inhibition. Its own product inhibits its activity. So as glucose 6-phosphate levels climb, hexokinase activity goes down. And that is to slow this first enzyme down so that the later steps of glycolysis are not overwhelmed. If hexokinase kept turning glucose into glucose 6-phosphate faster than the later enzymes of glycolysis could keep up, we would have this buildup of glucose 6-phosphate sitting around, all these reactive glucoses, highly negative, dying to do chemistry. And if we don't have subsequent enzymes in glycolysis to send that glucose 6-phosphate to, it's probably going to engage in chemistries we don't want it to. So hexokinase slows down as glucose 6-phosphate levels climb so that the first step of glycolysis remains on pace with the later steps. So once that glucose 6-phosphate is made, it's isomerized. So that's our second reaction type for step 2 of glycolysis, glucose phosphate isomerase. This enzyme also tells you what it does. It isomerizes phosphorylated glucose, which is exactly what we see here. We have the 6-membered ring, the Pyranos ring, converted to a 5-membered ring. We have one carbon coming out of the 5-membered ring here, and the other carbon coming out here, and it's still phosphorylated. So true isomerization reaction. No atoms lost, no atoms gained. The atoms have just been rearranged in the molecule. That is step 2. Glucose 6-phosphate isomerized to fructose 6-phosphate, and this is an unregulated step. Step 3, perhaps the most important step of all of glycolysis, catalyzed by phosphofructokinase. Again, the name tells you what the enzyme does. It is a kinase, so it phosphorylates things. And what does it phosphorylate? It phosphorylates already phosphorylated fructose. So this enzyme name is saying, as the enzyme, I take phosphorylated fructose and I phosphorylate it again. I'm a kinase that acts on phosphofructose. So here's that fructose 6-phosphate we just ended with in step 2. And ATP is once again our donor. This is the second ATP that we're burning in glycolysis. So we're at a 2 ATP deficit already, trying to make ATP, but we got to burn some energy to get there. And we have further activated this molecule. So we are left with fructose 1,6-bis-phosphate. That bis tells you that the 2 phosphates are on 2 different carbons, and the carbons are carbon 1 and carbon 6. So here's one phosphate, here's the other, here is the fructose. It's phosphorylated at the 1 and 6 carbons, so fructose 1,6-bisphosphate. And ADP is left over, just like we saw in step 1. ATP is the phosphate donor, and once that second phosphate has been donated to carbon 1, we're left with adenosine diphosphate there. Also, this is our second regulated step. Phosphofructokinase, or PFK, is allosterically regulated. It's an allosteric enzyme. It has a secondary site, and that secondary site can be bound by ATP. As ATP levels are high and ATP binds to phosphofructokinase, that enzyme activity goes down, which makes sense because the whole point of glycolysis is to make a little bit of ATP, but also to make pyruvate that we can ultimately feed into the citric acid cycle, that we can have undergo oxidative phosphorylation to make a lot of ATP. So you really don't want to be doing step 3 of glycolysis unless the cell needs ATP. And if ATP levels are high, there's really no point in doing this step. So if ATP levels are high, that ATP binds to the allosteric site of PFK, and PFK activity goes down to slow glycolysis down as well. So nice feedback of the ultimate end goal of aerobic respiration right here in step 3. And step 3 is referred to as the committed step. Once we undergo step 3 and we make fructose 1,6-bisphosphate, we're pretty much committed to going through all of glycolysis. So if we do that, if we catalyze step 3 and we make fructose 1,6-bisphosphate, the next reaction type that we have is a cleavage reaction. We take that 6-carbon sugar, fructose, and we cut it in half. The two things that we're left with is DHAP, or dihydroxyacetone phosphate. We see that here on the left. And GAP, D-glyceraldehyde 3-phosphate, GAP. These are the two halves of fructose 1,6-bisphosphate. And that cleavage reaction is catalyzed by an enzyme called aldolase. So again, aldolase cuts fructose 1,6-bisphosphate in half, leaving us with DHAP and GAP, the two halves of fructose 1,6-bisphosphate, a cleavage reaction. Now we take that DHAP and we isomerize it to another GAP molecule. So simply by rearranging the atoms on dihydroxyacetone phosphate, we can convert that into glyceraldehyde 3-phosphate. This sets us up for parallel reactions. We have one glyceraldehyde 3-phosphate already existing here from the cleavage of fructose 1,6-bisphosphate, and we've just isomerized DHAP into another glyceraldehyde 3-phosphate. So now we have two GAP molecules in glycolysis, two glyceraldehyde 3-phosphates, and they will be processed in parallel. So everything we talk about from this point on is actually happening times 2. So each of those two GAPs are going to be engaged in a redox reaction that ultimately phosphorylates them. This step of glycolysis is that 2-for-1 step. We are going to strip some electrons and protons from each of those two GAP molecules and put them onto NAD+. So in this case, GAP is being oxidized and NAD is being reduced. And in concert with that, simultaneously, we're going to be replacing some of those electrons and protons with a free phosphate. So we go from glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate. So we stay as a glycerate. We stay as this glycerate backbone. But now we add a second phosphate onto carbon 1. And what allowed us to do that is we've stripped a proton and some electrons off of carbon 1, and those unpaired electrons that were left behind, we used to make a covalent bond with this phosphate. Now the phosphate here is a free phosphate, so no ATP is being burned. We're using a free phosphate as this donor. So what reaction type is this? We'll categorize this as a redox reaction. That's really what's important here. The redox reaction comes first and it activates the rest of the reaction. If you want to be precise when and if this comes up on an exam and you want to say that this step is a redox and phosphorylation reaction, it's totally true. But I would caution you against just calling it a phosphorylation reaction because that redox component is very, very important. So again, we had 2 gaps coming into this step. We strip some electrons and protons from each of those gaps and use them to reduce NAD. That's going to be an electron carrier for us. And we replace those unpaired electrons with a free phosphate, leaving us with now 2 molecules of 1,3-bisphosphoglycerate, or 1,3-BPG. Each of those 1,3-BPGs is going to be used in a phosphorylation reaction. So this step is a phosphorylation reaction, but what's being phosphorylated is not the glucose metabolite, but ADP. So we're making ATP now. Remember, since we're doing this in parallel, and this reaction that you're looking at here is occurring with 2 molecules of BPG, we're actually making 2 ATPs over here. So we've just broken even. We burned 1 ATP in step 1 with hexakinase. We burned another ATP in step 3 with phosphofructokinase, or PFK. And now we've made 2 ATPs here in this step. So we're at net 0 for ATP loss or gain. And what we're left with on the glucose side of this reaction is 3PG, 3-phosphoglycerate, or glycerate phosphorylated only on the 3rd carbon. So, you're seeing the themes here, but the chemical names tell you the structure. They describe the structure. The enzyme names describe the catalysis. So if you're good at remembering chemical structures, then focus on that and they'll clue you in on the names. If you've got a really good memory, then focus on the names and they'll clue you in on the structures. There's such a wonderful relationship between the names of these molecules and their structure, and the same is true of the enzymes. This enzyme is called phosphoglycerate kinase. So that kinase tells you that it's a phosphorylation reaction, and the phosphoglycerate tells you what's involved. So this reaction is saying, hey, I'm involved in a kinase reaction that involves phosphoglycerate. Well, here's the phosphoglycerate, and the kinase reaction is with ATP. Truly, this enzyme is actually named after the reverse reaction, right? Because this is a single phosphorylated glycerate, and if you were to phosphorylate this, you'd go back to 1,3-BPG, but still the enzyme name is cluing you in on the very step that it's involved in. So to recap here, 1,3-bisphosphoglycerate, and there's 2 of those running in parallel, is stripped of its phosphate from carbon 1, and that phosphate is being used to phosphorylate ADP into ADP. Since we're doing this in parallel, we've just made 2 ATPs, and that breaks us even for glycolysis. Then we take those 2 3-PGs, those 2 3-phosphoglycerates, and we isomerize them. We're going to move that phosphate 1 carbon up. We're going to transfer that phosphate from carbon 3 to carbon 2. So 3-phosphoglycerate becomes 2-phosphoglycerate. And this is an isomerization reaction. Now, technically, when you just move a phosphate group, that's a mutase reaction, but we're not going to get so technical here. We're rearranging atoms, nothing gained, nothing lost. We'll call that an isomerization. Step 9. That 2-phosphoglycerate that we just successfully isomerized is going to be used in a dehydration reaction. So we're going to strip 2 protons and an oxygen from 2-BPG. That water is going to come off as a leaving group, and we will be left behind with phosphoenol pyruvate. This is essentially pyruvate with a phosphate group on it. So we're 1 step away from where we want to be in glycolysis. Again, this is a dehydration reaction because we're losing water in the process, and 2-PG, or 2-phosphoglycerate, becomes phosphoenol pyruvate. And that brings us to step 10. The last regulated step of glycolysis, that phosphoenol pyruvate, is involved in a phosphorylation reaction. That phosphate group that we see on the second carbon is going to be stripped and used to phosphorylate ADP into ATP, and that is going to be a net gain in ATP. Everything from step 5 on happens in parallel. Once we isomerize DHAP into a second molecule of glyceraldehyde 3-phosphate, everything's happening in parallel. So we're actually we're working with 2 phosphoenol pyruvates here in parallel. We're stripping each of them of their phosphate. We're phosphorylating an ADP in parallel. So we're making 2 ATPs here. And that's our net gain of glycolysis. Glycolysis nets us 2 ATPs as our gain. This enzyme name is also named for its reverse reaction. Pyruvate kinase, or PK, is the enzyme that we are using for this reaction. Again, it's really describing the reverse reaction. If we take this pyruvate and we phosphorylate it with a kinase, we're going to be left with phosphoenol pyruvate. But the enzyme name certainly clues you in on the step that we're dealing with. It's the only enzyme name in glycolysis that has pyruvate in its name. And step 10 is the only step that culminates in pyruvate. So right there, pyruvate kinase makes pyruvate. Pyruvate kinase ends glycolysis, whose job it is to make pyruvate. And this enzyme is also regulated by ATP, just like PFK is in step 3. As ATP levels climb, PK enzymatic activity goes down so that we slow down the last step of glycolysis and we don't make too much pyruvate. As ATP levels fall, pyruvate kinase enzymatic activity goes up, and we make more pyruvate because we need more ATP, and we feed that pyruvate ultimately into the citric acid cycle. So that is glycolysis. Now, if we back up and we just hone in on those specifics, step 1. Step 1 is a phosphorylation reaction. It's catalyzed by hexokinase. Glucose is phosphorylated to glucose 6-phosphate. And this is a regulated step controlled by feedback inhibition. Glucose 6-phosphate itself is the inhibitor, slows down the enzyme action. Step 2 is an isomerization reaction. Glucose 6-phosphate is isomerized into fructose 6-phosphate, and this is catalyzed by glucose phosphate isomerase. Step 3 is our second phosphorylation reaction. Fructose 6-phosphate is phosphorylated to fructose 1,6-bisphosphate. The enzyme is PFK, or phosphofructokinase, and this is our second regulated step. Phosphofructokinase is allosteric, and it is inhibited by ATP levels. Step 4 is our cleavage reaction. Here, fructose 1,6-bisphosphate is cleaved by aldolase into dihydroxyacetone phosphate, or DHAP, and glyceraldehyde 3-phosphate, or GAP. To set up for those parallel reactions, in step 5, that DHAP molecule is isomerized into a second glyceraldehyde 3-phosphate. So now everything we do from this step forward, we do in parallel. We have 2 gaps at this point, each of those gaps representing half of fructose 1,6-bisphosphate. And triose phosphate isomerase is the enzyme responsible for this isomerization. What a beautiful name. Triose, I work on 3-carbon sugars. Phosphate, those sugars are phosphorylated, and I isomerize them. Step 6, each of those 2 glyceraldehyde 3-phosphates is both stripped of electrons or oxidized and phosphorylated to create 1,3-bisphosphoglycerate. In this step, NAD is our electron carrier. It is reduced to NADH plus H, and a free phosphate is our donating group for that second phosphorylation on carbon 1. We move on to 1,3-BPG becomes dephosphorylated, and ADP becomes phosphorylated. So this is a phosphorylation reaction catalyzed by phosphoglycerate kinase. Again, we lose that phosphate group on carbon 1, and we use that phosphate to phosphorylate ADP into ADP. Since this is occurring after step 5, this is a parallel reaction, meaning everything we're doing here we're doing twofold. So we just made 2 ATPs, and we made 2 3-phosphoglycerates. Step 8. In step 8, we take those 2 3-phosphoglycerates that we just made, and we move that phosphate group from carbon 3 to carbon 2. technically a mutase reaction. We will call it an isomerization reaction, but the reason why I keep mentioning that mutase subcategory is because it gives us our enzyme name. Phosphoglycerol mutase is telling us that it takes phosphorylated glycerates and mutases them, or moves that phosphate. So again, 3PG becomes 2PG. That phosphate group moves from carbon 3 to carbon 2 by phosphoglycerol mutase. This is an isomerization reaction, and we are doing it in parallel. Step 9. We take those 2 phosphoglycerates and we dehydrate them. We strip them of an oxygen and 2 protons. When oxygen and 2 protons leaves as water, we are left with phosphoenol pyruvate, or pyruvate phosphorylated on the second carbon. This is catalyzed by the enzyme enolase. Eno for phosphoenol. So that too tells us what's involved in this reaction. 2-phosphoglycerate becomes phosphoenol pyruvate, and enolase makes phosphoenol pyruvate. And that phosphoenol pyruvate is then dephosphorylated. That lost phosphate group is used to phosphorylate ADP into ATP, and that leaves us with just pyruvate. Another parallel reaction. We had 2 PEPs coming into this. We dephosphorylated each of them. We phosphorylated ATP 2 times over, giving us our net gain of 2 ATPs, and the enzyme that catalyzes this reaction is pyruvate kinase, giving us our 2 molecules of pyruvate. Finally, pyruvate kinase is our third and last regulated step of glycolysis. It is also regulated by ATP levels so that we don't have too much energy on hand when we don't need it. So that is glycolysis in its bare bones nutshell, really zeroing in on the most important components: reactions themselves, reaction types, enzyme names, and overall purpose. That's the 4 main features we really want to be getting out of glycolysis. All of the tangential information that I give you in the lecture is critically important to understand the story of glycolysis. I'm not trying to say that what I'm saying in this video in only 20 minutes is all you need to know about glycolysis, but this is the canvas, this is the palette by which you can understand glycolysis. I would recommend that you learn what I've put in this video first and know it really, really well, and then go back to your notes and go back to the lecture videos to pick up those side features, those accents and flavor of the actual lecture, so that you have the context to understand all of that deeper information. Other than that, you know what to do. As soon as the dialog box pops up, if you have any additional questions or comments you'd like to make about glycolysis, please don't hesitate to let me know.